Good morning. Happy Monday. Dark, dreary, rainy, but still glad to see you, so thank you for being here and stuff, I know. Anyway, what we're going to do today, and at least part of Wednesday probably, is more review for the midterm. And Friday is midterm exam 1. When you come on Friday at 1:10, bring calculator, pencil, bring a note sheet if you'd like to, just like you use for quiz 3. The empirical formula lab we did on Friday. The one new thing, exam prep 1 worksheet. And this is in the companion right after the problem set 3. It's also online. If you'd rather, that's fine too. Exam prep worksheet is 1-page double-sided. Basically, the question is given, the answer is given for most of them, and you just show your work how you go from the question to the answer. I'm hoping that most of them aren't a big deal, but if you do see anything weird, let me know. We'll knock these out and stuff and take care of business. Anyway, that'll be due Friday, 1 o'clock. Also bring your goggles again, because this week's lab, percent potassium chlorate, is definitely one where we're gonna have flames and stuff like that. It's pretty fun. It's a great way to do something after a midterm, which I know you're just thrilled to be, but hopefully you can burn things and watch them bubble and stuff, and chemistry, Russell, whatever you want to say. Anyway, that'll be the goal for Friday. One other minor thing, we have science division meetings once in a while, and our first one is going to be this Friday. It's technically like 9:30 to 11, so I have to move my 10 o'clock office hour this week only. I'll move it to 8 a.m., so if you want to see me, come at 8 a.m., or I'll still have one at noon too, but the 10 o'clock I gotta move this week, so. Questions on any of this? Yeah.
We are allowed a motion on the midterm.
Absolutely, that's right. And same as before, 1 regular sized piece of paper, double-sided is cool, handwriting, don't do it. I love the notes that you guys used last week. It was really fun to go through them. If you want to reuse that sheet, come to my office on Wednesday or Friday. I can give it back. I'm not organized enough to do it today, I'm sorry, but Wednesday or Friday, that would be totally cool. If you think of things, let me know and stuff. But I guess without that, we'll just start the review. What the? So, yesterday was an important day in the chemistry world. October 23rd, 10 to the 23rd. And chemists call it the Mole Day. So let's think about wonderful, warm vacation spots while we suffer in cold silence. And happy Mole Day to you. Happy Mole Day to you. Happy Mole Day, dear students. Happy Mole Day to you.
How many atoms are you? Cha-cha-cha. That's 6.02. Cha-cha-cha. Times 10 to the 23rd. Happy Mole Day to you. How many moles of
This goes on for quite a while. I can send you the link to it if you'd like to see it and stuff later. But anyway, I couldn't do it yesterday, which was officially Mole Day. This was the first day I've seen you, but hopefully that shook everything up. Okay, back to regular scheduled programming. This is a kind of question that you might see on the midterm, all right? Just one of these is not correct. See if you can figure out which one is correct. I'll wait a couple minutes and stuff, and then we'll talk about the answer. If you've got your iClicker, start plugging away. If you don't worry about it. Just write down or think about what you think the right answer is. We'll talk about it and stuff. So. Yeah.
Are we still getting to use our note page during the midterm?
Absolutely, that's right. So bring that along. And if, John, if you want to use the one that you used on Friday, if you come to my office either Wednesday or Friday, I can get it back. I'm not organized enough to do it today, I'm sorry, but Wednesday or Friday, we'll make that happen. So.
Thanks.
Oh yeah, no worries, that's a great question. Everybody cool if I talk about this one? Yeah. Right. So all of these compounds listed, all right, regardless if the formula is right or not, are these compounds covalent or ionic? Ionic, well done. Now let's review that part real fast. Ionic, positives, negatives, true separation of charge, all right? Notice that none of these compounds have Greek prefixes. Good. Greek prefixes are the domain of covalent bonds, nonmetals plus nonmetals. So you're not going to see any Greek prefixes here. These are all ionic. Now, when it comes to ionic, the metals, there's two categories like we talked about. There's fixed charge metals and there's the variable charge metals. Variable charge metals, you need a Roman numeral. And none of these have Roman numerals on them, which is also good. Because if you look at these candidates here, calcium, sodium, magnesium, calcium again, and ammonium, all of these are what I would call a fixed charge ion, all right? Now for the metals, the fixed charges are 1A, 2A, and also the stairs. Aluminum, gallium, indium is the top step, zinc and cadmium second step, silver is the first step. So silver is the first step, +1, +2 for these two, +3 up there, et cetera, et cetera. So we don't have any Roman numerals, which is fine because these are all good. Now, ammonium is a polyatomic ion, and ammonium is always a fixed charge ion too. What is the charge on ammonium? +1, that's right, well done. So at this point then, we just have to start going through and breaking them down to figure out which is right and which is not right. And of course, a lot of these are polyatomic, so just FYI. Now, if you're still having issues with polyatomics, notice how 4 of the 5 have either ATE or ITE. And that inevitably means you have a polyatomic, and a polyatomic with oxygen. This is the only one that doesn't have ATE or ITE, and that's okay because this is just a regular ion, all right? It doesn't have polyatomics or anything like that. So calcium is a group 2A metal, +2. And if you know / memorize or look up what sulfate is, sulfate, SO4, -2. So when calcium and sulfate come together, don't leave any ions hanging, all right? +2 and -2 come together perfectly, no leftover charges. A is okay. Sodium nitrate, sodium group 1A, +1. Nitrate, NO3 is -1 when you look on the list. So that's also a great combination, 1 to 1, sodium nitrate, good to go. Next one, group 2A, magnesium, +2. Iodide, group 7A, all right? And if you look over here in group 7A, all of these, especially iodide, acetine, it's weird and stuff, but anyway, iodide, bromide, chloride, fluoride, 7 - 8, they're all -1, all right? And so iodide should be -1. You're going to need 2 -1s to balance the magnesium ion, which is +2. Magnesium iodide, good to go. We talked about earlier how ammonium is +1. If phosphate is a -1, this would be a great combination. Is phosphate -1? No, right on. Phosphate is -3. So if you have a -3 phosphate and you're combining it with a +1 ammonium, you're going to need 3 ammoniums to balance that out. So ammonium phosphate would be parentheses NH4 parentheses 3 PO4. That's because ammonium's +1 and phosphate is -3. So this one is not right. Calcium +2, hypochlorite is -1, so there's 2 of them. Good to go there. Any questions? Notice how, I just want to review this too. Notice how if there's only one polyatomic ion, for example, sodium nitrate, there's no parentheses, all right? It's not Na parentheses, NO3 parentheses. Chemists really hate writing things unless you have to, all right? So here with calcium hypochlorite or ammonium phosphate, parentheses are cool, all right? You've got more than one, like 2 CLOs, 3 NH4s, then you should use parentheses. But if there's only one, like on the nitrate or the sulfate, no parentheses. Any questions on any of that? Okay, so here's another question then that goes more along what we just talked about. And this one is a question basically of ionic versus covalent. And one of these compounds is not ionic. See if you can figure out which one it is. Looks like people are doing good on this. Anybody need some more time? Sweet. All right, there's several ways to do this problem. All right, the ultimate way, I suppose, is ionic means you've got positives, negatives. That means metals and non-metals. All right, so a lot of these are, most of these are metals and non-metals. But if you have something that's covalent, which would be the only option we have for not being ionic, then you're going to have just non-metals and non-metals. And another way is that, wow, this is the only one where a Greek prefix is allowed. Carbon dioxide is totally fine, all right? You've got two non-metals coming together. So you can either just look for the Greek prefix, which is what most of them have. The second one will always have a Greek prefix. First one, maybe, maybe not. A better way, of course, sulfur and oxygen are both up to the right of that metalloid line. So when they come together, the electrons are shared. Ionic, again, just means you've got true positives and negatives. That's a pretty strong force, but it's not always the coolest force to have. So. Cool. Eric, questions? Yeah.
When would the first element have a prefix? Like, it's okay if there was, like, say, S5O2, would it be, what was it?
Penta, sulfur, yeah, Your S5O2 would be pentasulfur dioxide, all right? Yeah, the first one, Clifford, only gets a Greek prefix if there's more than one. So
okay.
NO2, nitrogen dioxide, N2O, dinitrogen monoxide. So, excellent question. Yeah. All right, sodium oxalate has a formula Na2C2O4. Now, oxalate is a polyatomic ion. It's a one we haven't talked about as much, but we will later on. So based on this, what do you think the formula will be for iron 3 oxalate? Now, yes, you could put up Google and find the formula that way, but hopefully you can use this information to find the formula without using Google. That's kind of the goal. So see if you can figure out, based on the formula, maybe you know what oxalate is, this will be easy too, but if you can't, if you don't, and that's okay, think about what that tells you about oxalate, and then apply it to this thing to figure out the formula. So see what you can do. Everybody cool if I move on? Sweet. Okay, I have a PhD in chemistry, woohoo! And you'd think that I know it all. My mom made a comment about science, I think, but anyway, I don't need to display my personal problems in class. But anyway, you're gonna see a lot of polyatomics beyond the little list from the nomenclature lab, I'll let you know. And there are a lot of polyatomics that even I don't know. However, all right, let's say that Claire 10 years from now is working on a compound and she goes, oh, Dr. Russell, look, I've got sodium, blah, 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 and I have no idea what blah, blah, blah is. I can look, though, at the formula. And if there are two sodiums mixed with blah, 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 then I know that blah, blah, blah is a -2 ion, all right? And that's because good old sodium, unless you're in a lab, a black hole, middle of the sun or something, sodium is going to be +1. So based on the formula, all right, you can figure out that oxalate is -2. Now maybe you knew that already, which is totally cool too. If you didn't, that would be a cool way to figure it out. So -2 oxalate and iron +3. So we've got to mix those together so that you have a neutral compound. 3 +3 and 2 -2 come together. 3 times 2 is 6. So 6 divided by 3 means we're going to need 2 irons, and 6 divided by this 2, the -2 of the oxalate, means we're going to need 3 oxalates. So the formula here, Fe2 parentheses, because there's more than one, C2O4 parentheses 3. And that's a valuable thing because, like I said, there's a lot of polyatomic ions out there. And I don't know them all. I don't expect you to know them all. But this is a way then that you can figure out what the charge will be on the things. So, any questions on them? Cool. Here's some comments about ionic compounds, and they're all correct except one of them. See if you can figure out which of those 5 comments is not correct. Does anybody need more time on this one? All right. So, in future discussions, the strength between the positive and the negative parts will be pretty important to us. And in the problem sets and then lecture, I've been talking about what's called Coulomb's law. Now, Coulomb's law is something in physics you can use to actually calculate the forces between ions, blah, blah, blah. In this class and through Chem 223, we're just going to think about what the force depends on. And this alpha, which is really what it is, means proportional to. So the force depends on is how you can think about it. And over here, there's basically 2 parts that the force depends on. And the first one is the number of positive and negative charges. So I've been doing those crazy handshakes with people, all right? Single handshake is strong, double handshake is stronger, triple handshake, Claire, I haven't seen you forever. I'm not gonna really do it, but that's the top part, all right? So positive 1 is not as strong as positive 2, negative 2, positive 3, negative 3 would be stronger. And the other part is that it's inversely proportional to the distance. R is the distance between the two ions. So if I was shaking Claire's hand, I get farther from her, farther, 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 pinkies, and then finally even that's broken, all right? So as the distance R between the two gets bigger, this gets bigger, then the force gets weaker. So knowing that, all right, let's go through these. As the ion charges increase, the attraction increases. True, all right? And that's the handshake thing once again. Positive 1, negative 1, positive 2, negative 2, etc., etc. Positive 2, negative 2 is stronger than positive 1, negative 1, etc. Now, Coulombic forces make these three-dimensional crystal lattices. I showed some pictures of this in the lecture, but it's not just a sodium and a chloride. It's like a sodium, a chloride, a sodium, and a chloride, and it goes on and on and on in that dimension, but it also goes in the Y and it goes in the Z. It's literally 3 dimensions of these ionic interactions. So this is why ionic compounds are so strong. It's not just like one CO2 molecule. You've got this 3-dimensional kind of ionic lattice going of all these things, and that makes them for pretty tough. So B is true, all right? C, they're so strong that they become quite rigid. And sometimes even what we see, like in our world of these crystal lattices, is what you see on the molecular level. So I showed a quick video one time of a potassium bromide crystal, and it was very rigid, all right? And that's how the ions are created. They're also 3-dimensional. So very, very strong geology. This is a huge thing. D, positive, negatives attracted to each other. Absolutely, that's what makes this all possible. And then like people were finding, which was awesome, calcium oxide is a positive 2, negative 2 compound. Sodium chloride has a positive 1, negative 1. So NaCl would be like a single handshake, calcium oxide would be a double handshake. And calcium oxide is not weaker, it's stronger. That positive 2, negative 2 is going to make that a lot higher. Now this is the full version of Coulomb's law. In this version they use D instead of R, that's fine. There's a K constant, which in physics you can use to actually calculate these things. But again, what we're going to do in Chem 221 through Chem 223 is just talk about the factors that make the forces stronger. So we'll talk about numbers of handshakes, we'll talk about the distance between the ions. Any questions on that? Awesome. Okay. So here's a question. We've got 0.25 moles of each of the following, and the question is, which one of those will have the largest mass? Now remember, mass in my world is usually grams, all right? Could be kilograms, could be pounds, but it's mostly grams, all right? So think about which one of those would have the most mass if you have 0.25 moles of each of the compounds. people need more time on this problem. Okay. All of these examples here will look like this. We've got moles, you want to find grams. So you're going to need to look at the periodic table. And carbon is the easiest to do in my head, so that's why we're going to do this. But you want to take the moles and multiply it by the molar mass. So carbon is about 12 grams per mole. We have a 2 sig fig number, so I'm using 3 sig figs. 12.01 would be fine here too. But again, you only need to keep the sig figs going. So essentially 1/4, which is what 0.25 is, of 12 would be 3 grams of carbon. So that would be the mass for carbon. And you could go through and do each one of these, which is fantastic. But if you want to be the lazy chemist, and hey, who doesn't? Molar mass, all right, this number right there from the periodic table is going to be proportional to the mass you get out. So when you look at these 5 elements here, do we want the largest molar mass or the smallest molar mass? Largest, that's right. The bigger number here will create the bigger number there. And usually molar mass is proportional by the atomic number, so you want the largest atomic number. Zinc is number 30 on the periodic table. It's the biggest atomic number. So iron's 26, 13, 20, 12, et cetera, et cetera. So if you had to guess on a problem like this, yeah, go for the largest, either the largest molar largest atomic number or smallest atomic number, and definitely it's the largest one here. So yeah, so 65.4 is the grams per mole, the molar mass of zinc. Multiply it by 0.25, and voila, 16 grams of zinc would be the largest of these numbers. So you can see what the other ones are right there. So again, you could do each one of these individually, and that's totally cool. But if you want, if you think a little deeper, molar mass is proportional to the mass you get out. Good to go. Any questions on that? Okay. All right. This is kind of an interesting application of the things we've learned so far. This is a question where it says, find the average mass of one chromium atom. Now you have, between the periodic table and good old Avogadro's day, which was yesterday, you have everything you need to solve this. So play with this a little bit. Think if the answer is not E, darn it. See what you can do with it. We'll talk about it here. people want more time on this one?
I'm good.
Okay, it looks like I'm gonna start talking about it. You can ignore me if you want. Okay, this is kind of interesting because we talk a lot about, of course, grams and moles going to molecules and atoms and stuff like that. But using just the tools we have so far, you can actually find the mass of one chromium atom. Now, average is one of the key words here because the red numbers on the periodic table, including 51.9961 right there, those are the average masses in grams of a mole of the compound. So for example, 51.9961 grams of chromium would give you a mole of chromium. And we talked about how these numbers reflect the isotopes. So for example, there's a lot of chromium-52 running around. So 51.9 rounded up, 52, all right, there's actually quite a bit. I used to work with chromium-53 a lot, which was another isotope, not as abundant as 52, and there's a 51, et cetera, et cetera. So one kind of interesting thing you can do, well, from my perspective, is realizing that this is the grams in a mole of chromium, an average amount of chromium, and good old Avogadro's number is always 1 mole, 6.022 times 10 to the 23rd. So for this problem, because it's chromium, that would be the number of atoms in a mole. And if you multiply those together, you can see how the moles cancel out. You've got, you're gonna end up with grams per atom. And it is an average atom because the chromium number, 51.9, that represents all the things known. So if you multiply these together, you do get answer A, 8.634 times 10 to the minus 23rd grams. So that would be the mass of an average atom of chromium. And one type of question you could see is it'll give you a bunch of masses, and which one of those is too small for chromium? Well, if you had a number that was under this, that would be an impossible mass, in theory anyway, for chromium. Because that would be below what the average was and stuff. But anyway, 6.022 times 10 to the positive 23rd is Avogadro's number. I see once in a while some people trying to use 10 to the minus 23rd, and I understand. It's a huge number, and that means positive, big powers of 10, all right? This number right here is one we'll use in chapter 6. That's actually Planck's constant. It doesn't have grams per units, but we'll see that number here coming out. Anyway, this is just kind of an interesting thing to do. If you're a chemist anyway. Questions on?
So it's just the molar mass of chromium times Avogadro's number?
Well, you would divide by Avogadro's number, Alexis. You need this number in the denominator, all right? So in my world, multiplying this number would be on top, you know? So divide by it, and you can check yourself too, because the number you get, the grams of an atom, should be really, 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 really small. If you got a huge number, if this was on top, you wouldn't think that one atom would have a massive mass, you know? So helps me sometimes to think about it, to make sure I'm dividing, not multiplying, and stuff like that. Excellent question.
So in this scenario, you would recommend setting it up like that instead of using kind of like where we cross out moles and atoms and stuff like that?
Yeah. So notice how I crossed moles out, all right? Like the mole here is canceled by the moles right there. And at the end, my units, I'd have grams on the top and I'd have atoms on the bottom. So that would be the mass per atom is how I would do it. So yeah, whichever, any of these ways would be fine and stuff, so yeah. But if you want to, you could just, you know, divide and put 6.022 10 to the 23rd right there, and that would be fantastic. Yeah, Patrick.
So when it comes to the average mass, you're looking for the amount of atoms, or the grams per atom.
Grams per atom, that's right. It's not number of atoms, but it's the mass grams per atom. And it's the average mass because this number is the average of all the isotopes known.
So the atomic, isn't that called the atomic mass, the 51?
So you can also use AMUs, that's right. That would be the average AMUs of the atom. And if you have the AMUs to grams conversion, which honestly I don't have off the top of my head, but that would be an alternate way to get to this number too, yeah. That's not a number that I know off the top of my head, and I don't expect you to know, but if you've got it there, heck yeah, that would be another way to do this problem. You bet. Good call. Other questions? This is a question that'll pop up on the midterm, and it's just how to find percent composition of a thing. The mass percent would be an alternate way to talk about it. So see if you can use the fact that you've got carbon dioxide, and you essentially want to find percent carbon and percent oxygen in carbon dioxide. See if you can figure out how this process works.
How was your weekend?
hard time for this problem? Okay. So the way that I would do this problem is the first step, find the molar mass of the compound, all right? Now, molar mass for carbon dioxide, you would go to the periodic table, look up carbon, that plus 2 times oxygen. So carbon is 12.01 grams per mole to the 100th, which is what I usually do. Oxygen to the 100th, 16.00. So 32 from the 2 oxygens plus 12.01, the molar mass, 44.01 grams per mole. We'll use CO2 a lot, not as much as water, but almost as much. Not because CO2 is in greenhouse gases, although that's part of it. CO2 is a complex product. But anyway, 44.01 is the molar mass. Then the percent of carbon would be the grams of carbon in CO2. So CO2 has 1 carbon, and that carbon is 12.01. And if you take that and you divide by the molar mass, 44.01, multiply it by 100, that'll be the way to find the percent carbon. And you can do the same thing for oxygen, but because it's CO2, you have 2 oxygens, and each oxygen is 16.00 grams per mole. So 2 times 32, and you divide once again by the same value, 44.01, multiplied by 100%, good to go. So in this problem, carbon comes out to be 27.3%, all right, the way I did it. And I guess I only used 3 sig figs, okay, whatever. And oxygen doesn't say only 6 figs, so anyway, bad chemist. Anyway, oxygen then would be 2 times 16, that's where the 32 comes from. Again, dividing by the molar mass, 44.01. 72.7%. Now, if you have one percentage, you don't really have to do the second one. You can just go 100% minus the first one. So that would be an alternate way to find oxygen if you know carbon, or carbon if you know oxygen already. But again, first step, finding molar mass is pretty cool. So hopefully about this time you're seeing there's 2 ways to find these mass percents. There's this way, which is molar mass on the bottom and what goes into that particular element on top. But the other way is what we did in lab on Friday. Like we had, I don't know, 2 grams or whatever of the copper chloride, and on the top to find the percent copper, you put how many grams of copper we're collecting. So you can put grams of what you're looking for divided by grams total times 100. That's a more experimental way. This is a way, if you know the formula, you can then quickly find percentages and stuff based on things. So, any questions on that? Okay. We may not have enough time to do this today, so we'll take this up on Wednesday, all right? But this is the same kind of problem. We have percentage of one atom, but not the other one. So you can use those percentages to turn them into grams and then moles, find the empirical formula, blah, blah, blah. But that's more fun than we need right now, so we'll do that on Wednesday. Thank you for being here. Have a wonderful day. See you on Wednesday.